the very last thing I'm going to tell you about are another fun source of problems that made me in the past. Those are normalization forms.
I have my next guest come up here. I told her, I don't know how to introduce you. I have so many things I could say about you, but I don't know how. And she said, just say it's Rosa. And here we are, Rosa. Thank you so much.
Perfect. Okay, so for those of you who don't know me, my name is Rosa. There is where you can find me. I work at 37 Signals. I've been there for the last 7.5 years, and I'm really happy to be here. So I love these conferences. My partner said that I may love Ruby conferences more than Ruby itself, which is kind of not wrong. But I love the conferences because I think this community is really, really incredible. And out of all the conferences, I go to a lot of conferences. I use my vacation days to attend them. I love them so much. And out of all of the conferences I attended last year, which was a lot, I think Friendly.rb was my favorite. And so, I mean, can you imagine another conference where one of the speakers, Gabriela, she made crocheted brooches for people, and she just handed them out with the conference logo. Like, how cute is that? So yeah, thanks to Gabriela for doing that. And so I wanted to thank a lot Adrian, Stefan, Alex, Lucian, and Jacob for trusting me this year to speak here. Like, it's truly an honor to be part of your favorite conference. Okay. And I have to also thank Adrian for trusting me with the topic because it's sort of catchy title, like inspire strong feelings on you, but the talk is basically an excuse to talk about the strings. So this talk came out of how I usually learn a lot of things for my job. Usually I love bugs, not the bugs themselves, but I love investigating bugs. And so I use bugs a lot as an excuse to learn about a topic. So, you know, when you find a bug that you don't know very well how to solve, and then you go deep into a specific topic there and you start learning. So that's usually how I do learn new things. What happened with strings, encodings, and all those problems is that the amount of different things that you encounter when you get deep into this topic is kind of overwhelming. Like it took me quite a while to get the feeling I really understood what was going on when I faced those errors. So for a while, whenever I hit an encoding error in Ruby, I will just call like force encoding, UTF-8, I replace everything with the question mark and whatever. And then I move on, right? But always I have this uneasy feeling of not knowing what is going on, like not knowing what I'm doing. So last year, I actually took a step back and made a point of actually learning the fundamentals of all of this. And this is what I brought, a summary of all this is what I bring you to this talk. So we'll see first some facts along the talk. We'll see some facts you just need to accept. You cannot change. We'll learn some fundamental concepts and a little bit of history about why those are the way they are. And we'll see how this all come together in Ruby. And then, of course, we'll see some examples of real bugs and how we solve them. So let's start with fact number 1. This is computers only understand bits. For this talk, we'll mostly talk about bytes. So the bits will be grouped in bytes of 8 bits. But this is how it is. You cannot store text. You cannot transfer or send anyone text. You need to send bytes, and you need to store bytes. So humans don't communicate with bytes. We use language, we use text. So we need a way to translate bytes into text and vice versa, right? This mapping is what we call an encoding. And so one of the first encodings is called ASCII, and Probably you are familiar with this one. ASCII stands for American Standard Code for Information Interchange. It was published in 1963. It used 7 bits to represent each character. In total, it could represent 128 characters, and out of which only 95 were assigned to visible characters. And this is how it looks like, all the ASCII table now. And the reason it used 7 bits is because it was originally designed for machines called teleprinters that only supported 7 bits, but then it was used for computers. So what happened is that at that point, like later, general support for 8 bits was pretty much generalized in computers, so you had a spare bit there. So people, of course, started wondering, what to do with that spare bit. Can do something, since we can only represent 95 characters. So people started using that bit for other stuff. This is what is known as ASCII extension or code pages. People started to use it to represent other characters, and they come up with a lot of different code pages, and of course, all of them were incompatible with each other, like a lot of them. From that, this one may sound a little bit familiar to you. The ISO published one of them, the 88591. This was an ASCII extension that included support for Western European languages, and it removed the control code as well. The first characters in ASCII are control codes that were used in the past, for those teleprinters machines, but they weren't really used for computers. Then that one. And then they added the control codes back there, and they renamed the language to ISO -88591. So you can distinguish between the two without any chance of confusion. And this is this character set is what is also known as Latin 1. And then the ISO continued publishing many more extensions, but this is one that still prevails to this day. And this is how it looks. So you see that it's twice the size because they use the spare bit. It has those characters and some of them not used in the middle. Then Windows came and they say, okay, there is 2 rows here we are not using, so we put those characters there, that they fill all the space. And then with this, basically, we've reached the limit of what we can represent with 8-bit, right? There is no more space left. So because there were so many extensions and code pages, and it was very confusing, the original ASCII was renamed to US ASCII, so there was any problem. And then, meanwhile, in Asia, you can imagine, this didn't work at all, because in Asia, languages in Asia have thousands of characters, so they cannot use just 256 to represent all their languages. So they have other sort of encodings and systems, like DBCS, JIS in Japan, like a lot of this one. All of them also incompatible with each other, and incompatible with ASCII, and everything was compatible. So this more or less worked, more or less, as long as you didn't move strings from one computer to another, or as long as you didn't speak multiple languages in the same computer. But the problem is that with internet, when the internet just became generalized, everyone started moving strings from one computer to another. So that brought chaos, right? So this brings us to fact number 2. So we need more than 8 bits. We need to represent a lot of different languages that humans use to communicate. We also need emoji, which are the pillars of modern communication, as you know. So we need a solution that can, handle all this. And this is where Unicode comes. So Unicode is a standard that aims to unify all human languages, present, past, and make them work with computers. That's what it is. So the main component of Unicode is a char set, a character set. This is a group of characters. In general, a char set is a group of characters ordered, and each one with an identifier assigned. The identifier is known as a code point. And this is not, like a char set, is not an encoding. It's just a mapping between the character, like the abstract idea of a character, and that unique identifier known as code point. Until now, with ASCII, we map a character, like Latin capital letter A, we map it directly to its representation like in the computer, like in bits, right? But with Unicode, we get the concept of a character. Each character in Unicode is identified by a unique name that is written with capital ASCII letters, and that is mapped to another identifier which may not have anything to do with the way you represent this in your disk, or like how you store that, and that is known as code point. So we have this one. So the code points in Unicode, they are always represented with a capital U from Unicode, a plus sign, and the number of the code point in hexadecimal. That's usually how you will see them. And then, so Unicode is really, really big, it's huge. It gets continuously updated. Now we are in version 15.1. It defines about 1.1 million code points, and out of them, only 150,000 are assigned as of now, so we still have a lot of place for languages. Right now, it covers 161 scripts. That is also include, symbols for maths, music, of course, emoji, which are growing always. And then it also Unicode, besides the char set, it defines lots and lots of rules about how the characters interact with each other, and a lot of other things. So in Unicode, this is just the last thing I told you because I will use this later, the characters are divided in planes. Each plane uses 16 bits, so 2 to 16 code points. There are in total 17 planes. They are numbered from 0 to 16. The plane 0 is a very important one. It's called the basic multilingual plane. And then each plane is divided in blocks. The blocks don't have a fixed size. Some of them has many hundreds of characters. Some of them have just a few. And then they also have some private areas, like some blocks that are not assigned. It's guaranteed they won't be ever assigned. And people use those for languages that Unicode doesn't support by itself, like Klingon or the Tolkien languages or that. So yeah, so there are some blocks of Unicode reserved for that. All this is all very well, but how we store the code points, right? I say that the code points, they are not directly related to what you store in your disk or your memory or what you transfer. So how? So we need an encoding, obviously. And then we enter UTF-8. This is the king of encodings. UTF-8 stands for Unicode Transformation Format, and the 8 is the size of the minimal code unit used to encode characters, which in this case is 8-bit. It was introduced in '93 by Ken Thompson and Rob Pike. Those also are the co-authors of the programming language Golang, so they are very, very good contributors to the world of computing. And one important thing about UTF-8 that is different from ASCII is that it's a variable length encoding. So each character can take, so each code point can take from 1 to 4 bytes. So not all characters have the same length. And Unicode also introduced UTF-16 and UTF-32 that I will talk about later. So you were maybe wondering, so how does this work, like a variable length encoding? How do you know when a character starts and when it ends and when the next one starts and ends, right? How do you traverse a string like this? So let's see it quickly. It's very neat and very clever how they implemented this. So remember we are trying to represent all the code points in Unicode. So for code points from 0 to 127, from that, we are going to do the same as ASCII. We are going just to store the code point as if it was like in the bits. So just 1 byte. So for example, if we have those code points with the word mochi, those are, you see, they are all from 0 to 127. So we will just store them as ASCII will do, right? Like this. That's one. And then from 128 onwards, we are going to use a variable number of bytes from 2 to 4 bytes. And we will do this using some bits to indicate that we are starting a new character. We are going to use the first byte, and we are going to start that with as many ones as the total number of bytes in the character, and then a 0. And then the next bytes are called continuation bytes. They start always by 1, 0, And then the remaining bits we can use to store the character. Let's see with a quick example. So if we have a 2-byte character, you can see we have the structural bits here, and then those will be used to store the actual value of the code point. So that will be the non-structural bits. So we have 11 bits there, so we can represent a 2 to 11 number of characters. And then following the same idea, we have 3 bytes, and then we do the same thing. We have 16 bits there, and 4 bytes. We will have 21 bits, and with that we can represent by far the whole. You remember Unicode defines 1.1 million, so we have enough with 4 bytes, and that's how it works. Let's see a quick example of a string that contains characters over 127. So we have this mochi with a little fancier, playful characters, and those are those Unicode code points. And some of them, here is how we will represent this using UTF-8. You can see that some of them take one byte, for example, the parentheses or the C and the H, those are just ASCII. And then some of them takes 3, 4, depending on the code point value. So yeah, and very interesting feature that comes for free with this implementation is that UTF-8 has error detection built in. Why? Because check this. Like we know that if we get this sequence, we know that the first byte is always a leading byte. So we know that it has as many ones as total bytes in the string. So if we see this, we are expecting the next byte to be a continuation byte because we know this is two bytes. This is a 2-byte character. What happened that we find here at 0? It's not, right? So this is invalid already, like you cannot have this in UTF-8. So this is a way you can have, unfortunately, not the only way you can get an invalid byte sequence in UTF-8. So the fact number 3, now that I talk about invalid strings, is that encoding is out of fun. Like you cannot have a string, you cannot have text without knowing what encoding is using. Like you cannot represent it properly unless you know the encoding. Otherwise, you just have bits, but you don't know how to represent those. So yeah, you need to, how do you know? Because you just have the bits, so you need to be told or you need to guess. So for example, imagine you get those bytes out of nowhere. How do you know how to represent this? Imagine if you assume you are using ISO 88591. So then this is España, which is my country. It's all cool, but the same one, if I didn't know and I guessed UTF-8, you will get this, right? So this will be invalid. And the same with this other sequence, if I use UTF-8, it will be okay, it will be España, right? But if I try to decode the same one with ISO 88591, then I will get this. And usually not knowing the right encoding, like having the wrong encoding, is usually the source of the majority of problems related to encoding. Like assuming it is so common that there is even a word in Japanese to represent this. Here it's called mojibake, and it's the result. It's basically the result when you get like gibberish characters or garbled text, which is the result of choosing the wrong encoding to represent something. Yeah, mojibake, I think it means character transformation or something like that. So I say you need to be told. How are you told about the encoding? There are many different ways. So for example, in HTTP, you have the content type header. You can have a meta tag with a char set. In email, you get the encoding embedded into headers. There is specs. There are some languages that use like the spec, or the RFC tells you this. You need to use UTF-16, for example, for this thing. Or there are magic comments. You remember in Ruby when if you are old enough and switch from Ruby 1.8 to Ruby 1.9, and you have to start putting the encoding UTF-8 on the top of the file. So this is like to tell the language that this file is using UTF-8. So this is how you do it. And okay, let's see all this for all the theory. So let's see how Ruby implements strings. So Ruby is a very interesting language in that sense because Ruby stores the bits in the string, the bytes, and it stores also the encoding they are using together with the string. This is not the case for many languages. Don't know if you know, but for example, JavaScript, Java, C#, they all store characters using UTF-16. So they transform everything and they store it assuming UTF-16. But in Ruby, you don't transform before storing. You just actually store the encoding and the bits. So this means in Ruby we have an encoding class. You can check it and you can see how many encodings Ruby defines. I think the IANA, the Internet Assigned Numbers Authority, identifies about 258 different encodings on internet right now. And then with Ruby, you have, as of now, you have 103, which is usually enough, unless the one you need is not there, which may happen. Some of them have aliases like this, and that you can check via the names. And some of them are dummies that you shouldn't use directly. And then you can also, if you have a string, you can ask for the encoding like this. Then let me show you some really useful methods that you can find in Ruby to inspect strings. You may have used chars before. Maybe you didn't know about code points or bytes. But they are very handy. You can check the chars, you can check the code points. Those will be the code points with the format in Unicode, with the U and the number in base 16. And then you can also check the bytes, like this, or in X. Then code points, I've been talking about code points in the context of Unicode, but there are other char sets, and code points among them, they are not universal, like they differ. Like imagine we have this word with UTF-8, and then the same with a different char set. Some of the code points, you can see they are different. Usually when some of the code points are the same, that means both probably extended ASCII and those characters are ASCII. And yeah, the same with other different characters. Okay, so let's see how we can, in Ruby, inspect and manipulate a string's encoding. So I already talked about encoding, where you can see what encoding a string is using. You also have encode, and this is the most important. Like I will show you a few methods, and if you live with something, just remember this about these methods. So encode will try to transcode the bits, and will also change the encoding to the one you are passing. Force encoding, however, won't touch the bytes. It won't touch the string, the bits you actually have there. It will just change the encoding assigned to that string. Then scrap, it will replace invalid bytes for the encoding you have, and it won't touch the encoding. And then finally, you have a valid encoding that you can use if the encoding you are using has a way to detect whether the bits are valid or not. Like in the case of UTF-8, that's the case, but we will see that there are other encodings where they just don't have a way to say whether the bits are valid or not. And with that, let's see the first bug. This one, I didn't actually investigate myself. It just came to me as a learning. JP Camara, he's a very prolific Rubyist. He opened a pull request in SolidQ a few months ago. He said, yeah, with socket get host name, I'm getting an error when I try to store it in the database. I'm getting this error, the undefined conversion error of that character from ASCII 8-bit to UTF-8. Okay, so let's try this. I tested it, of course, before reviewing the pull request. So I checked the host name in my machine to this, like with an apostrophe. And I check it in the Ruby console, and yeah, I see you see some strange, usually that's what you get, that's the X representation of the character, and that's usually what you get when because the terminal in Ruby is by default in UTF-8, so if those characters are not visible in UTF-8, that's what you get, usually just the value of in X of those. So then I check the encoding, and yeah, it's ASCII 8-bit. This name, ASCII 8-bit, you may have found that in Ruby, is a bit confusing because it has the word ASCII in it, but it's actually not ASCII. It's better to think of this encoding as unknown, of just binary data. Those are just bytes. Like you don't know what they correspond to. Like they could be, even if you read like a JPEG file, for example, you get bits. They don't correspond to any encoding. So that's this format. And yeah, actually, if you check the names for this ASCII 8-bit, you can see that one of the aliases is binary. Okay, so in this case, we have those characters there, and we know that those 3 bytes actually do represent the apostrophe character in UTF-8. So let's just say, okay, this string you think is using binary, but it's actually UTF-8. So if you will force encoding, remember, force encoding doesn't touch the bytes, just change the encoding. So we get this. And yeah, so this, notice the difference with encode that will try to translate the bytes to the encoding you are passing. But it doesn't know. Ruby doesn't know how to translate from binary, because binary doesn't carry any meaning. It doesn't know which, you just see the bytes, but you don't know which code points in UTF-8 those bytes are representing. So you cannot do that. You cannot translate them. But notice that also valid encoding for this in binary is true, because in binary anything is valid. Like there is no rule. You just have bytes. So that's why valid encoding sometimes is misleading. Because I've seen sometimes in problems with using, for example, ISO 881591, anything is valid there. Like you just have any value for those bytes is valid. So people are, this looks wrong, but valid encoding returns true, right? Because it's valid, it's just not correct. Like how you check it. So you can actually translate from any ASCII string. This works if you try to translate everything that is usually ASCII. So you have also this handy method, like ASCII only, that is sometimes useful to know whether you can translate easily between some encodings. If those are ASCII compatible, which is usually the case, so in that case you can translate. And this, as a bonus, this was something that it was caught me with another kind of bug where it took me quite a while to figure out, and it was very strange, which is if you have a string and you encode it and decode it using base64, you lose the encoding there, like it changed to binary. So it was a little bit, I had a little bit of fun with that, using that to send a token in authentication headers. Usually you need to base64 encoding and decode it, so I didn't realize it was losing the encoding there. So now I will tell you very quickly about UTF-16. Remember that there was another encoding introduced by Unicode. This one, remember the basic multilingual plane? First, when Unicode started, it was thought that with the basic multilingual plane, with those 16 bits, they will have enough for all human languages. So in the beginning, there was only this. And they have another different encoding, this one, that used always 2 bytes. And then they realized it wasn't enough with 2 bytes. So this evolved into UTF-16, which is also a variable length encoding. The difference with UTF-8 is that the minimum code unit is 2 bytes. So each character has either 16 bits or 32 bits. So you use 2 bytes. So here, how do we represent this? This is also a fun one. So for the basic multilingual plane, we just store the code point as it is, as a number. So this means this is actually incompatible with ASCII. And then the other planes, we use something called surrogates. And we use the 2 code points are called a surrogate pair. The surrogates go to, is a specific design range in the basic multilingual plane that goes from D800 to DFFF. And you can see it here. This is all the basic multilingual plane, and you can see there the little surrogate range. So this means that we will use either, the one code units, so 16 bits, and then the 32 for the 2 surrogate pairs. So let's check how this looks for the string that I used before, this one. In UTF-16, we can see that each character takes 2 bytes this time. We have to pad it with zeros there. And there is one of them that takes 4 bytes. So that is, check the bytes, there is the 835 DCBE. Those are in the surrogate range. And all the other characters take 2 bytes in this case. And below is the example in UTF-8. So you can see how the bytes are different. And then UTF-32, just very quickly, this is the simplest of the bunch. You just use a fixed length. Each character takes 4 bytes. So it's just the code point value, you store it, and that's it. It's the simplest. Okay, and another thing very important to know is that the code points across all the UTF-8, 16, and 32, they are the same, because they are the same char set. They are representing the same char set. So you have the same code points. But the bytes aren't the same, because they have a different underlying storage there. You can see that the bytes are totally different. And then also the size. And this allows me to introduce also byte size, which is very useful in some cases when you can check the size of a string and it returns more characters. That some people confuse the size in character with the size in bytes. So the size in bytes is actually because some characters take more. So you can see that the byte size is different. And that brings us to the next bug, a mysterious high surrogate. This arrived when I was at work, and we got this ticket from one of our SRE team members. He was saying he was working on a migration from MariaDB to MySQL 8, and he ran into an encoding error. In Basecamp we have a boost table, and there was a row that they couldn't store back in MySQL 8. And he was asking, okay, can you help me fix it? And so my colleague, Jeremy, who is an Oracle, he knows everything, like really everything. So he said, this is from Jeremy, he said, yeah, these bytes, these are the truncated height surrogate of a UTF-16 character, whatever. And I was like, I didn't know what this was. So I took this as a chance to learn what surrogate pairs are, what is all this. So let's see how we can put everything we learned until now to find out why this is a high surrogate. So let's check. Those are the mysterious bytes, and let's check them in binary. So we have those three sequences, and we can see the structural bits there, and they look right? You have 3 ones, that is a 3-byte character, and then the leading byte, the continuation bytes start with 1 0 as dictated by the specification. And then we have this. So let's see how this we are taking here. Here I'm taking the ones not in yellow, so actually the bits that store the code points. And yeah, and we convert it to exit, and what do we have there? We have a code point in the surrogate range. Those cannot be by themselves in UTF-8. They are invalid. So this is another way you can have like an invalid sequence in UTF-8. If you get a code point that is valid, but it doesn't correspond to any character that you can encode on its own. So that is how he knew. And then how to fix it. It's easy. We just get it, we screw it, because in that case we cannot fix it for real. We don't know what the low surrogate was, so we just have to screw it. And then now it has a valid encoding, and then we save it, and that's it. And the very last thing I'm going to tell you about are another fun source of problems that made me in the past. Those are normalization forms. These involve strings that look the same, but aren't equal. Like maybe you have run into this in the past. But anyway, imagine you have those 2 strings, like they look equal, but they aren't. So why? Let's check the encoding. Maybe the encoding is different. No, it's the same. Okay, let's check the code points. Okay, here we are. So we have different code points. Why this? Okay, the first one is just 1 code point that corresponds to this character, like the Latin capital letter A with ring above. And then the other 2 code points are those 2. Those are the capital letter A and the combining little ring, that one combining little ring. So these are actually 2 different characters that are equivalent. So the first one all together is called the canonical composition, and the other one is called the canonical decomposition. Right? And you find this in many different characters in European languages. All the ones that have accents and stuff that you add to letters, usually they have 2 forms in Unicode. So actually the A with the little ring above has a, well, here's how you can see it in Ruby. In Ruby you have Unicode normalized, and you pass the normalization form you want to use, and you can see if they are actually equivalent or not. And the A with the little ring has a 3rd form, actually, just out of curiosity, is the Armstrong sign, which is a length unit, and it also has another code point, but thankfully, if you normalize it, it will tell you that it's equivalent to the other 2. And just the very last bug we have with this, it was the case of the invalid signature. Okay, so we got a ticket from our support team saying that some emails from a specific sender, they weren't rendering the images. So they sent us the email, where the images weren't rendering in our email service. We have an email service, so this was out of that. In our email service, we run a proxy for the images, so we don't reveal the IP address of the recipient to the service that is hosting the images. So then we checked the URLs for the original image and the proxied image in our case. And my colleague, Jacopo, he noticed the URLs were slightly different. Like you can see I put it in red, the characters that are URL escape, but they are a bit different. So we check those characters, what actually they represent, and this one, and they are the same. Like it's just the O with a cute accent. And so yeah, we check this one. So we check one of them, and it turns out one of them corresponded to a different normalization form. So why? Why was that was one of the URL we were passing to the proxy, but why? Where was it being changed? So they took a bit of debugging, and we trace it to a call deep into addressable URI that we were using to normalize the URL before passing it to our proxy. So that was the culprit one. It was changing the normalization and using always the canonical form, the composition form. So how did we fix it? So we just stopped calling that, and yeah, that was it. And this is how I learned about normalization forms. And yeah, and the fact number 1, which is number 4, which is not for this talk, but in life in general, there is never time to tell everything. Unfortunately, there are lots and lots of things with strings, Unicode, and all that, like lots of things. It will be material for many different talks. So just to take away with you from here, remember that computers only understand bytes, even though AIs may make think the opposite, but it's not true. Like underneath, everything is bits, is 1 and 0s. Strings don't make a lot of sense without an encoding. You cannot represent that properly if you don't know what encoding you are using. Although, like so sometimes you don't know the encoding, and you have to guess. I would say UTF-8 is a very good guess. Like right now, about 98% of websites, for example, are using UTF-8. This wasn't true 20 years ago. 20 years ago, this was way more wild. And then the last thing, which you can apply to strings and to anything else, just go always deep and try to understand the fundamentals of what you are dealing with, because it really helps a lot. And yeah, I compile a list of really good resources there. Ruby, also encoding related, that I recommend to check out. And yeah, and that's it. And so some of you may know that I have a little dog named Mochi. I bring her to conferences a lot because she's already been to 5 tech conferences or so, because I'm hoping she can do my job one day. But unfortunately, I couldn't bring her here because I came with Wizz Air and Ryanair, and they don't allow dogs. So instead, what I did was use an idea from my friend Alex, who is there, I think, and I brought some Mochi stickers. So if you want some, I got them here, if you want some stickers. And that's it.